Background and history. Inception and purpose. The mission to study the Sun's polar mysteries. 1. The solar orbiter was conceived to provide unprecedented views of the Sun's polar regions, unlocking new insights into solar dynamics. 2. The mission aimed to complement existing solar observatories and expand our understanding of the Sun's behavior. Scientific objectives: probing the mysteries of solar polar regions. 1. The solar orbiter's primary goal is to study the Sun's polar regions, where magnetic fields play a crucial role in solar activity. 2. Understanding the Sun's polar behavior has implications for space weather predictions and our comprehension of stellar processes. Collaborative endeavor: international cooperation in solar exploration. 1. The solar orbiter is a collaborative effort between NASA and the European Space Agency (ESA), showcasing the power of international partnerships in space exploration. 2. The joint mission brings together expertise from both agencies to maximize scientific returns. Historical impact. Advancing solar science: contributions to our understanding of the Sun. 1. The solar orbiter has made significant contributions to solar science by providing detailed observations of solar structures and activities. 2. The mission has enhanced our ability to predict and mitigate the impacts of space weather on Earth. Solar orbiter in the solar fleet, a key player in solar observation. 1. The solar orbiter joins a fleet of solar observatories, contributing unique perspectives and data to the collective understanding of the Sun. 2. Its role in complementing other solar missions solidifies its significance in advancing solar physics. Unprecedented solar views: breaking new ground in solar imaging. 1. Solar orbiter's imaging instruments capture high-resolution views of the Sun's polar regions, offering a level of detail previously unattainable. 2. The mission has provided scientists with an up-close and personal view of solar phenomena. Historical milestones. Launch and deployment: setting the solar orbiter on its journey. 1. The successful launch marked a crucial milestone, propelling the solar orbiter on its mission to study the Sun. 2. Deployment and activation of instruments signaled the beginning of scientific observations. First solar encounter: proximity to the Sun for groundbreaking observations. 1. Solar orbiter's first close approach to the Sun allowed for unprecedented observations of solar features. 2. The initial encounter provided essential data for researchers to analyze and interpret. Orbit adjustments: fine-tuning the trajectory for optimal observations. 1. Precise orbit adjustments ensured that solar orbiter could capture the desired views of the Sun's polar regions. 2. The mission's flexibility in orbit demonstrates its adaptability for targeted observations. Technological advancements. Heat shield technology: protecting the spacecraft from solar intensity. 1. Solar orbiter's advanced heat shield technology allows it to withstand the intense heat near the Sun. 2. The heat shield ensures that the spacecraft's instruments remain within operational temperatures. Remote sensing instruments: capturing multi-wavelength solar data. 1. Solar orbiter is equipped with a suite of remote sensing instruments, capturing data across multiple wavelengths. 2. These instruments enable scientists to study different layers and aspects of the Sun's atmosphere. Solar wind analyzers: studying the solar wind up close. 1. Instruments on board solar orbiter analyze the solar wind, providing insights into its composition and dynamics. 2. The detailed analysis of solar wind contributes to our understanding of its impact on the solar system. Challenges and risks. Extreme environmental conditions: navigating the harsh conditions near the Sun. 1. Solar orbiter faces challenges associated with extreme temperatures and radiation levels in close proximity to the Sun. 2. The spacecraft's design and technology must withstand these conditions to ensure mission success. Data transmission challenges: transmitting data from distant solar orbits. 1. Solar orbiter's orbit takes it far from Earth, presenting challenges in data transmission and communication. 2. Overcoming the limitations of distant communication is a critical aspect of the mission. Instrument calibration: ensuring accuracy in solar observations. 1. Calibrating instruments for accurate observations in the harsh solar environment is a complex task. 2. Precise calibration is essential to ensure the scientific validity of the data collected. Future prospects. Extended mission objectives: expanding the scope of solar exploration. 1. Solar Orbiter's success opens possibilities for extended mission objectives, potentially including observations of other celestial bodies. 2. The spacecraft's capabilities may be harnessed for broader contributions to heliophysics. Collaborative discoveries, sharing data and insights with the global scientific community. 1. Solar Orbiter's data is shared with a broader scientific community, fostering collaboration and diverse perspectives. 2. The mission's discoveries contribute to the collective knowledge of the Sun's behavior. Advancements in solar prediction, impact on space weather forecasting. 1. Insights from Solar Orbiter may lead to advancements in space weather prediction, benefiting satellite operations and astronaut safety. 2. The mission's data may contribute to improved models for forecasting solar events. Controversies and debates. Privacy and security concerns, managing sensitive solar data. 1. Debates may arise around the privacy and security of solar data, especially if it has implications for Earth's technological systems. 2. Balancing transparency with security is a key consideration in managing solar information. Funding and prioritization, debates on the allocation of resources for solar exploration. 1. As with any space mission, debates may arise regarding the allocation of funding and resources for Solar Orbiter. 2. Prioritizing solar exploration against other scientific endeavors may be a topic of discussion. International collaboration standards, aligning protocols for collaborative space missions. 1. International collaboration in space missions brings forth discussions on standardizing protocols and practices. 2. The Solar Orbiter's joint mission nature may spark debates on the harmonization of international collaboration. Additional information. Educational outreach, Solar Orbiter's impact on science education. 1. The mission contributes to science education through outreach programs and engagement with students. 2. Educational initiatives associated with Solar Orbiter aim to inspire the next generation of space scientists. Public engagement, involving the global community in solar exploration. 1. Solar Orbiter's missions are shared with the public through outreach events and engagement initiatives. 2. Involving the global community enhances public awareness and appreciation for solar science. Solar Orbiter vs. Parker Solar Probe, a comparative analysis of solar missions. 1. Comparing Solar Orbiter with other solar missions, such as the Parker Solar Probe, provides insights into the different approaches to solar exploration. 2. Understanding the complementary nature of various solar missions enriches our overall understanding of the Sun. Fun facts. Solar Orbiter's unique orbit, traversing the Sun's polar regions in a distinctive trajectory. 1. Solar Orbiter follows a unique trajectory, allowing it to observe the Sun's polar regions, which are challenging to study from Earth. 2. The spacecraft's orbit is optimized for capturing unprecedented views of the Sun's polar dynamics. Solar Orbiter's instrument names, quirky names for cutting-edge technology. 1. The instruments on board Solar Orbiter have names like SPICE, spectral imaging of the coronal environment, and STIX, Solar Orbiter heliospheric imager, adding a touch of creativity to scientific exploration. 2. Naming instruments in a way that is both descriptive and memorable highlights the human side of scientific endeavors.